Modern applications demand high-throughput, fault-tolerant systems that can reliably deliver data between services in real time. From financial transactions and sensor data to social media feeds and log pipelines, message queues form the backbone of asynchronous communication in distributed systems. This document presents a comprehensive design for a distributed message queue system, inspired by technologies like Kafka, RabbitMQ, and Pulsar. It covers everything from the core concepts, like partitions and consumer groups, to deep dives on replication, storage layers, and delivery guarantees. Whether you're building a new messaging platform or trying to understand how large-scale message queues work under the hood, this guide aims to provide a clear, scalable blueprint. What you'll learn: how to model topics, partitions, and consumer groups, strategies for leader election, replication, and state storage, trade-offs between at most once, at least once, and exactly once delivery, how message routing, batching, and offsets enable high performance and fault tolerance. Let's dive in. The problem is to design a distributed message queue system like RabbitMQ. Here are some good requirement questions to ask. What's the message format and average size? Can messages be repeatedly consumed? Are messages consumed in the same order they were produced? Does data need to be persisted? What's the delivery semantic? At most once, at least once, exactly once? What's the target throughput and latency SLA? Let's walk through the high-level design of a distributed message queue system. This architecture is foundational to systems like Apache Kafka and underpins high-throughput messaging pipelines. Topic and partition. At the core of the system is the concept of a topic, which is a logical category for messages. Producers send messages to a topic, and consumers read from it. Each topic is split into partitions, which are the basic unit of parallelism and data distribution. Each partition behaves like a FIFO queue, ensuring ordering within that partition. Broker. A broker is a server that holds one or more topic partitions. Brokers are the data carriers in the system, persisting messages and handling client requests. Offset. Every message within a partition is assigned an offset, which acts as its unique identifier and helps consumers track where they left off. Message routing and keying. When a producer sends a message, it chooses a partition for the message. If a key is provided, all messages with the same key go to the same partition. This enables ordering guarantees for related messages. Consumer and consumer group. On the consumer side, we have consumer groups. Each group consists of multiple consumers, and the partitions are distributed among them. This allows for parallel consumption while maintaining exclusive consumption of a partition within a group. Importantly, different consumer groups can independently consume the same topic, each maintaining its own offsets. Storage components. Data storage persists the actual messages within each partition. State storage manages the current consumption state, like offsets per consumer group. Metadata storage stores topic configuration, partition assignments, and broker info. Service discovery and leader election. To manage the distributed environment, we need a service discovery mechanism to know which brokers are alive. A leader election protocol ensures that one broker acts as the controller, handling administrative tasks like partition assignment and broker coordination. This architecture supports high scalability, fault tolerance, and flexibility in message consumption patterns, making it ideal for real-time data pipelines and event-driven systems. Let's dive into the core technical components of our distributed message queue system. 1. Data storage. Our system is both write-heavy and read-heavy. To support this, we use a write-ahead log (WAL) mechanism. Messages are written to disk as append-only WAL files, ensuring durability and crash recovery. WAL provides high write throughput and is optimized for sequential disk access. 2. State storage. We store the mapping of partitions to consumers and also maintain offsets indicating the last consumed message for each consumer group. This allows us to resume consumption from the correct point after failures or restarts. 3. Metadata storage. We maintain configuration and topic metadata separately. This includes topic names, partition counts, replication factors, and retention policies. This metadata is typically stored in a highly available configuration system like Zookeeper or etcd. 4. Message structure. Every message has a key, value, topic, partition, offset, and timestamp. The key helps in partition assignment. Messages with the same key go to the same partition for ordering guarantees. 5. Batching. Batching is implemented in the producer, broker, and consumer to strike a balance between latency and throughput. Larger batches increase throughput but may add delay. Smaller batches reduce latency but increase system load. 6. Producer flow. The producer sends messages to a routing layer. The routing layer determines the correct leader replica for the partition based on the topic's replica distribution plan. Once the leader receives the message, follower replicas pull the message for replication. After a quorum of followers acknowledges the replication, the leader persists the message and acknowledges the producer. 7. Consumer flow. Consumers use a pull-based model. They request messages from the broker starting at a specified offset. This allows for flexible consumption rates and backpressure management. Consumer rebalancing is handled automatically to distribute partitions evenly across consumers within a group. Again, Zookeeper plays a critical role in maintaining group membership, consumer assignments, and offset tracking. This architecture ensures fault tolerance, scalability, and consistency while providing high throughput and low latency, key requirements for modern distributed messaging systems. Let's deep dive into the replication and partition strategy, which ensures scalability and fault tolerance in a distributed message queue. Partition replication. Each topic is divided into partitions, and each partition has multiple replicas, one leader and several followers. The leader replica is responsible for all reads and writes for that partition, while the followers passively replicate data from the leader. Producer behavior. Producers send messages only to the leader replica of a partition. Once a message is received, the leader waits for follower replicas to synchronize, that is, replicate the message, to a configurable degree before sending an acknowledgement, ACK, back to the producer. In-sync replicas, ISR. The replicas that have caught up with the leader are known as in-sync replicas. The in-sync definition can vary by topic configuration. For instance, a follower may lag behind a few messages and still be considered in sync. Producer acknowledgement settings, K. Producers can configure how many ISR replicas need to receive the message before considering it successful. K asks all. Guarantees strong consistency. No message is lost if enough replicas are up. KSR1 reduces latency, but if the leader crashes before replication, data can be lost. KSR0 fastest, but no reliability. Useful when durability isn't critical. Consumer behavior. Consumers always read from the leader replica of a partition. They rely on the partition leader mapping and will adjust as needed. Partition scaling. If the number of partitions changes, for example due to scaling out, producers are notified so they can adjust routing logic, and consumer groups must rebalance, redistributing the partitions among consumers to maintain an even load. Delivery semantics. The system supports various data delivery guarantees based on ACK settings. At most once, KR0, fastest but not reliable, no retries. At least once, KRs1 or all, retries on failure, may lead to duplicates. Exactly once, requires idempotent producers and transactional semantics, more expensive, but guarantees no loss and no duplicates. This design balances trade-offs between latency, throughput, and durability, giving system architects flexibility to optimize for different use cases.